Yeah, in the previous video, I have stopped at slopes, design of slopes. Now we talk now in this video design of size of the stream channel, and then of course time required, how much area it covers, and some other aspects. So uh, let us go back to our PowerPoint presentation. Uh, so design criteria of under border strip irrigation comes now size of the irrigation stream. Irrigation stream or waterway size depends on the infiltration rates of the soil and also width of the border strip. So infiltration rates of the soil and width of the border strip. For example, if you have say coarse structured soils with high infiltration like sandy soils, definitely requires a very large stream to spread water, the two only small lengths of the border, to cover the entire strip rapidly. See, in this case, right from the beginning, we are telling we have to cover the strip as quickly as possible. Avoid any excessive losses due to deep percolation. That is very important, particularly at the upper reaches. So these are the in the case of coarse structure soils, this is a problem. Suppose in the case of fine texture soils, they are having a low infiltration. They require only small streams. Why? To avoid excessive losses due to runoff at the downstream. So at the end of at the end of the downstream, deep percolation at lower reaches occur. Fine texture soil like clay. So size of the stream depends upon the soils, its texture, and its infiltration characteristics. The next table will give you the total gamut of the picture. You can see in sandy soils with this infiltration rates are given in this column, and soil types are given in this column. Then border slopes also given in this column. Then how much is the size of the uh, supplying channel? I mean discharge. So many liters per second. Okay. So for example, if you observe for sandy soils with different slopes, as the you know percent of slope increasing, there is a less discharge because it will move faster. That is why less discharge. If the slope is not so much, then a little bit greater discharge. Same is the case with the loam sand. So more discharge towards lesser slopes and a little bit more discharge towards the more slopes. Likewise, all the soils same, but across the soils, if you observe, if you see across the soils for the same slopes, for example, clay at the bottommost for the almost slopes of 1.1 to I'm sorry here 0.20. Then if you observe, it is a little over 2 liters per second, whereas for the same slope for the sandy soils much higher. So normally clay loam and clay requires less uh, discharge of the stream, whereas for sand and loam sand, you will get more discharge of the stream. So it means stream size depends upon the infiltration rate of the soil and its slope. Uh, then we will take the time required, how much time it requires. For example, given the discharge, given the area, and then what is the time required. So there is a small derivation. Of course, I am not showing due to paucity of time. It's a simple derivation. the relation between size of the stream and time rate of water application over a given area of land can be easily stated by many of rational equations given below. So this is T equal to 2.3 y by I log, of course, base 10 q by q minus IA. What is all these things? Area of the A is the area of the land covered at any time T. Area of the land covered at any time T. This is the time in area in hectares. In hectares, area in hectares. And I, rate of infiltration of the soil is given so many meters per hour. And Q, quantity of water in hectare meter per hour. That is the discharge. And T, time in hours. Y is the average depth of sheet of flowing water in meters. So if you have these parameters, you can estimate in how much time you can cover an area for a given discharge. So that is the relation. What is that? How much time it will take for a given discharge of the channel to cover an area. Of course, given that the soil characteristics like infiltration rate and of course how much depth you want. Okay, so let us see with a figure also. I think you can see this is how this is a supply channel. This is how the area is covered in a time t. Of course, these are the borders. So this is analysis of time in border strip method. So this is a relation. Let us take an example also. You can see what is the time required to cover an area of 0.2 hectares when a well is discharging at a rate of so and so cumex, that is 0.4 cumex for irrigating some rabi crop. And of course, the average depth of the flow is expected to be 5 centimeters. Average infiltration rate of the soil may be taken as a 2.5 centimeters per hour. So you can see the given, what are the, as per the earlier equation given, this is the equation of course, Q is given, so many cumex 0.04 and then that is converted into hectare meters per hour, and then Y centimeters, depth, that is the depth of water required, and that is converted into 0.05 meters, and then I, infiltration rate, centimeters per hour, again converted into so many meters per hour, and the area to be irrigated is 0.2 hectares. So simply substituting those parameters in this equation, and just time required with the given parameters is 0.8507 hours. So this is how you can calculate. Before I finish this, border strip irrigation, we try to go see some of the intricacies of the low discharge and then high discharge and so on. Let me end this PowerPoint. Then we'll go for some yesterday's FAO publication I have given to you. They have given nice figures also. You can see, can you open this? Yeah. See, if you have a cross slopes, as you can see, if you do not have a uniform slope across the border, if you have just a cross slope like this, how water is simply flowing the slope, following the slope. So that you should avoid these cross slopes. Throughout its width, the border should have uniform slope throughout its width. That's the one thing. Another important point I would like to highlight. Suppose stream size is too small. What will happen compared to the required soil infiltration characters and its length and so on? If the stream size is too small, you can see the water is simply get infiltrated here. The front, water front will not move. it is wasted in the deep percolation. So you must design such a way that water should advance very quickly. Then to that matter, you have to reduce your length, reduce your width, whatever it is, that has to be done. So this is very important, another important point. Then stream size, if it is too big, what will happen? You can see the quickly it goes without covering much of the strip of the area, and goes as infiltration to sideways. So this is also a problem. Suppose if you have a bigger stream or a bigger discharge, you can increase or decrease the length suitably based on the soil infiltration characters. So that's why design of a stream based on the available stream, and then you should quickly fix the length and breadth of the uh, border strip as per the you know uh, calculations. You cannot simply just have a something and then let it go. No, it is not correct. So of course, other things are irrigating a border. Of course, not figure also not so. So this is how in actual figure irrigating a border. These are the two borders you see. So this has finished your border strip irrigation at length. Then we will go for the next one, basin irrigation. I think I will stop here this video, and then we will meet in the next video with what is known as border basin irrigation. Okay, thank you very much.